should start. I'm very happy to announce today's Thursday afternoon speaker, Erik, who will tell us about multiple zeta values and deformation.
Thank you very much. Thanks for coming. Thanks for letting me be here in the first place. I must start with an apology, because if you look at the bottom of the slide, this is an old talk, and already at the time, it was not the first time I gave a talk. So if you have seen this talk, feel free to run away. There's going to be nothing new in this talk, this version of the talk. But I was encouraged to speak about this, and so I assume that you came here to listen to this. So my project is trying to be very basic and try to explain the main ideas. So I will not go into too many technical details. If you have questions about technical details, we can talk about that afterwards. But by all means, the most important thing is that you interrupt me and ask questions in the spirit of this morning. Trying to build bridges and not leave people behind. So, I'm talking about joint work with my collaborators, Peter Banks and Brent Lim, which is in deformation quantization, which hasn't featured that much in this kind of conference. But it's another place where number theory and physics talk to each other. Problem with quantum physics, there's many different versions of what people call quantum mechanics, quantum field theory, and so I'll be trying to explain in what sense I mean quantum here. But the main idea is what is illustrated on this first slide, that you want to make sense somehow of this transition to go from classical mechanics to quantum mechanics. That's the quantization, at least in the classical sense. And somehow in the meantime, this transition, at the moment there seems to be no other way to get this transition done without introducing transcendental numbers. And this is a kind of recurring theme. I will get back to that later in the talk. So just to paint the pictures of in classical mechanics, so that's the world where I think about you're describing particle or maybe a pendulum or thing like that. So you have finite degrees of freedom, number of parameters that completely describe the state of the system. So position and momentum, these are just numbers, and they compute. There's no question, but they could possibly not compute. But when you go to quantum mechanics, things become operators, and some things become non-competitive. There's uncertainty principles, and so it's this transition how to take the product and make it a non-competitive product, which is where the magic happens. So let's try to summarize some of the key aspects of this transition. I'm talking about very first kind of quantization principle, which is called canonical quantization, which can be formalized as follows. So on the left-hand side, you start with classical mechanics. And here the idea is you're describing a system with a finite number of degrees of freedom. So your space that parameterizes possible states is a manifold in general, or an R to the N. It's a very simple case. If you have a single particle moving on a one-dimensional manifold, particle state is completely described by two variables, position where it is, and the momentum or the velocity which is moving around, then you know exactly what's going on. And then physics is supposed to tell you how the state evolves over time. If you know the state in one moment, you should know it later. So there's an equation, a differential equation that tells you how the system evolves over time. So F is any observable, F could be the position, the momentum, could be the energy, whatever. And the rule is, in the Hamiltonian formalism of classical mechanics, that the time dependence of this thing can be computed by a certain bracket operation with a special function that's called the Hamiltonian. Very special function that tells you what is the actual physics. So you have the background geometry, the space of parameters, which in this case is just a free, but of course, if you imagine a more interesting topology, but I'll be interested not in topology. I will have a boring topology. I will always be on R to the N. So no interesting topology. But still, even if you're on a fixed geometry, you can have different Hamiltonians. You can have different potentials, electric fields, magnetic fields, whatever, that affect your particle. So they will come in by changing this Hamiltonian, which is a way to package the energy, kinetic and potential energy of the particle. And then this simple formula tells you how the Hamiltonian dictates how things develop over time. So what is this bracket? That's what's called a Poisson bracket. I will get back to that in more detail, but it's an operation that is extra data. So you not only have your space with that parameterizes the variables of the state, but there's also some operation that allows you to take two functions on your space and wiggle them together and make this bracket out of them. So that's another function. And this is a classical analog of what will later be the commutator of quantum mechanics. This will be a key player. I'll get back to it in a second. At the moment, it's just a rule that takes two functions and they gives you another. And this rule, this bottom bracket, has this property that it's somehow already very reminiscent of quantum mechanics. If you take position and momentum, these are called classical mechanics, that are like a canonical pair of quantities. So their bracket is 1, it's not 0, and it's going to be reflected on the right side. So let's go to the right side, quantum mechanics. What's different if I take a particle on R1 moving around quantum mechanics? The situation is a bit different. So here, the state is not just the number x and the number p, but you have what's called a wave function, and which tells you that the particle may be here or there. If it's more likely here, a bit more likely there, but you get these kind of pictures. I should have written R here, not R2. So you have like this probability distribution of how a particle might be spread over space at a given time. So that's different. Another thing that's different is position momentum. So they're not variables, they're now operators. And then what you're talking about is an expectation value of operator. So if you have pick an operator like position momentum, and you pick a state, wave function, then you can form an expectation value. What is the expected value, expected eigenvalue for that operator in that state? And you can see if you have a byte like this, the position operator is just the average of position. So if you have a byte, the expectation value of position will be somewhere around here. The expectation value of momentum will be by a Fourier transform. In this case, probably similar, but depending on the curve, it can be very different. And you have these familiar commutation relations with position momentum operators. And this is the Schrödinger equation written in a slightly different form for expectation values, where the time dependence of this expected value of the position momentum is the commutator, or is the expectation value commutator of the operators that correspond to the function. Any questions on this kind of very naive idea of quantization, taking functions of phase space, turning them into operators, which is what we want to do. And somehow, on the right-hand side, things are rather difficult. You want to make things precise because you have to field space and scalar product, and there's all kinds of technical challenges to make rigorous quantum mechanics. And so a cheap way out is to say, well, let's maybe not focus on the right hand so much. Let's try to stay on the left side, but still capture one of the key features of the quantum world, which is this non-commutativity. The fact that these operators not compute.
Question?
Yes.
These brackets, the diamond brackets around the left hand.
These here? Sorry, so this means expectation value. I should point. Okay. Sorry for the empty Zoom audience. This is not on. Can they see me on the camera?
It's fine.
So if you have this expectation value of an operator, I should rewrite the subscript here for a state. Let's say I have a wave function psi. Right, and what you do is you complete the integral over all R. You take your state psi, you act with the operator. Sorry, I have to write this notation. You apply your operator and then you send it again. If you think of scalar products, it's a scalar product of psi which then applied to psi. Yeah. So I have a wave function which tells me how the thing is spread. Then I apply an operator, whatever it is, you can take position, you can take momentum, you can take any combination of this. And you form this is the expectation value. And I just write this with these angle brackets here as a shortcut. Its idea is that this is what on the quantum side is equivalent to what is the momentum of the particle, what is the position of the particle. It doesn't have a position momentum of operators, but for a given state you can form the expectation value that is the error. And then if you have an eigenfunction, it actually has a sharp eigenvalue corresponds to perfect, but in general. This is what all the angle brackets do. If you take the Schrödinger equation and apply it to the same bracket really get very easily this commutator in there. Okay, look. So the one key thing I want to keep of this is this analogy that somehow the fact that the position momentum operators do not commute, that it's this IX bar with the Planck constant here, that's somehow an equivalent to this Poisson bracket of the coordinates not being 0. So some of the ideas you want to write the commutator of the operator on the quantum side. Somehow it seems like on this picture that they're just the same as if you first compute the Poisson bracket on the classical side and then take the corresponding operator. Which means, so first of all, this is not true. It's correction terms. You cannot rigorously implement this. This only works to the first order in H bar. But to the first order H bar, you can actually make it work. And then there's one piece of this puzzle missing. Right? On the left-hand side, we have a product of these functions in phase space, which is commutative. On the right-hand side, the product of the operators is not commutative, only becomes commutative in the limit when H bar is 0. H bar non-zero is not commutative. On the left-hand side, we do have the analog of the bracket, Poisson bracket, but we don't have an analog for the actual product of the operators. As if I take the non-commutative product of the operators corresponding to the classical observables, then my question is, what is the classical thing whose operator analog would be that? And this is what the star product is supposed to be. Yeah, so on the quantum side, we have this product, we kind of pull this product back onto the classical side under this quantization. And now I want to understand this, the star product, just the classical way to note it from the start. This is what this talk is about. How do you get the star product on functions on R to the n that turns this Poisson bracket into some actual product? So in the beginning, we started with physics and quantization, and now it's purely mathematical problem. So no physics from here on. What is the mathematical formalization of this program, which is a very old program? So the input, what is the bare input data, right? So in the most general case, you have some space of states. I'm only taking R to the D. So let's say we have a classical mechanical system R to the D. Remember, there's another ingredient, which is the Hamiltonian, which fixes a particular energy that tells how things move. But that's choosing a particular physical system. Here, I'm only talking about this Poisson bracket. So I haven't really told you what this Poisson bracket is. So let's try to formalize what are the requirements of this Poisson bracket. First of all, it has to be odd. So if it has any chance to be related to the commutator and the operators, it better be antisymmetric. Also, if it's supposed to correspond to a commutator, it better has the algebra structure. So we want a Jacobi identity. And then the other identity is this Leibniz principle that you want, and by the symmetry it holds in both arguments. So it acts like a derivative each slot. And I guess a physicist would say that somehow it's something to do with locality. Because if you work out what this means, that somehow only depends on the derivative of the first derivatives at a point. Just really take the value of the Poisson bracket at a certain point does not depend on the functions far away, it depends on how they vary. These are kind of the axioms. And the classical Poisson manifolds come from symplectic geometry. And then what is deformation quantization supposed to do? It's to take this as an input, and what we want is now a product. We want the star product on the space of functions on R to the D. You already see there's some caveat here. I'm taking formal power series in H bar. I don't want to worry with convergence issues, which is a super complicated issue. It doesn't have a simple answer. My talk, I will forget about convergence, then there is a simple answer. Well, not quite that simple. And what do we want from the star product? Well, it's better be a product, so it has to be associative, because the product of operators on the quantum side is associative. We definitely want that. We want it to be a quantization, so if you turn off quantum, if you set h bar to 0, it should be the original product. One thing to start with the commutative product, then some correction terms. And also, we want that this product has anything to do with the Poisson bracket, such that when we form the commutator of the subproduct, you actually get Poisson bracket. So this is the commutator of the subproduct. This should correspond to Poisson bracket up to higher orders. So physicists doesn't have problems with corrections of higher orders. As a mathematician, you might want to maybe we can actually get rid of those and really have a strict h bar here, but you can construct counterexamples even fully normal. Just as. So this is the problem. This is the input. I want the subproduct. And it turns out it's actually it's pure algebraic question. You want to solve these constraints. But in principle, first it's not even clear that there is a solution. I mean, there's obviously a solution to the second equation because you just define it like that. Find the bf times d plus something times h bar. Okay. Second is easy to solve. Third is also easy to solve. You just define the next term to be the Poisson bracket. So what's the problem? The problem is you want associativity. If you work this out, this gives you a big system of quadratic equations among these operators. Because here you're plugging at a certain order h bar, you already used some of these operators. Now you're plugging t and h in there, multiply with f, but that should be the same as plugging f and t in there, multiplying with h. So you get a big system of constraints of differential operators. And because it's not linear, I mean, it's not clear that it even has a solution. So then the famous result of Panzer was in the paper of 1997, that it is actually possible to always do. So no matter what Poisson structure you start with, you can always find at least some star product that quantizes it. Of course, there's immediately the question of the mathematicians, well, there could be another solution. What is the modular space for quantization? This has also been studied. There's an example, Panzer. Talk about it later. For the moment, I just want to explain this one solution and how it came about. And it's a rare case where there's actually an explicit formula. It's not just an abstract existence result. It's an explicit formula. Just this, that, here you have the stop. So let me explain to you this formula. This is it. Yeah, so the nth term that comes with h bar to the n in this formula power series is given explicitly as the sum of certain graphs. It's very reminiscent of Feynman graphs. If you're familiar with this setup, forget about this tutorial. It's a finite sum of graphs. I will explain what kind of graphs in a second. And it has two parts. For every graph, you have a differential operator, which acts on the functions that you're multiplying. And it also depends on the Poisson bracket on your space. And then there is a coefficient. And you have to choose the right coefficient. Otherwise, the thing doesn't work. So let me just show you the graphs. So these graphs have two types of vertices. So I will draw one of the blue ones. There will always be two of them that will be at the bottom. It's always two blue vertices on the bottom. And then there's a couple of black vertices above. And the number of black vertices is the order in h bar. So the first order in h bar would just be this one graph. There's nothing else. If you have two black vertices, there are these four things you do. Because there's some extra rules, you're not allowing any edges going to the same. You're not allowing two parallel ones. You can have an anti-parallel thing. That's the part. And the other rule is that every black one has two edges going out. That's very important. And with these rules, you only have these four things. There's nothing else. And so this way, for every n, you can write down a finite list of graphs. And then for every graph, I have to tell you how to get its v and how you get its w. Then you can compute your favorite stuff. Okay. So what are these ingredients? What is this differential operator? I can see it here, very good. So you should have told me.
It's okay.
It's okay.
Okay. On the previous slide, are you allowed in-house so directed loop?
go directly
Two,
to
but
this here.
yeah, that alone, that would be allowed.
That's a lot of this,
Okay.
and it's needed. For some time, people thought you can get rid of these, but you can't. So let me
Why
explain.
do you put these arrows down?
Well, the thing is, you have to have two outgoing arrows. You cannot have both do the same. That's not allowed, right? So at least one of them has to go to. Okay. I mean, actually, you're right. I could draw another thing. I could have drawn this arrow also to the left, and have this blue empty. In principle, I could have done that.
Weighted.
But then you can show that if the graph is not connected, the weight will be 0. So you can restrict this to connected graphs, so that it's really important. Now for these operators, so I've chosen this example with two internal vertices. So we want to construct a differential operator that acts on two functions and somehow involves the star product, the Poisson bracket. And the rule is very simple, as you see here. So for every black vertex, we put a Poisson bracket there. The two blue vertices, there's always two on the bottom. One is F, the other is G. And then every arrow becomes the differential. So remember, we are on R to the D. We have a canonical basis, x1 up to xt. It makes sense to take partial derivatives with respect to x1 and xt. And then you match them all together. So for every vertex, you get a term. So let's say this Poisson bracket, you just take the Poisson bracket of xi and xj. This is another internal vertex, so you have a Poisson bracket there, but it has an incoming edge. So it gets a derivative. And remember, every vertex has exactly two outgoing edges. You know, one is associated to one argument, the other is associated to the other argument, and then you take the derivative exactly with respect to the same variable that you put as it's partial j because it's xj. So if I'm going to be really precise, then actually every internal vertex, you know which is the left and which is the right edge. So really have this there. And then you only have two more terms. You have f and g, and f gets two derivatives, two edges coming in, so I and k. That is only a single derivative of g. And then you just sum. So it couldn't be any simpler than that. So for every graph, you don't know how to write down this operator. No magic there, but there is actually quite a lot of magic because these operators, they form these graphs that form a nice operad. So you know how you can insert one graph into the other in a way that respects exactly the Leibniz rules, like the differential operators on each other. That's to show the star properties. But we will not need it. I just want to show you, show this so that you see actually how the graph, Poisson bracket, and the function of differential operators come in. But for the rest of the talk, I want to focus only on these integrals.
Sorry,
Yes,
after
go ahead.
if I choose the standard based on the symplectic space, so that the Poisson form is just the usual 0, 1, minus 1, 0, I get rid of a lot of graphs here, right?
Oh, yes.
And is there an easier way?
Very, very good question. So this formula, you know, you can write it down. But now, say your example of the classical symplectic structure. It has a property that the Poisson bracket itself is constant, at 0, 1. Right? So all the derivatives of it are 0. So every graph where you have an edge going into black vertex is 0. So what's left over? So all the edges have to go to the blue vertices. And you can only have at most one edge. Two parallel edges are not allowed. So the only graph you can do is where you have the two blue vertices, F and G. You have a bunch of black vertices, but they can only have edges to the ground. So you only get this. And what is this? Well, the operator is for every term, right? You have xi, xj, say xi1, xj1, and you make xi2, xj2, and so on. And then you have ei1, ei n of f, and then ej1, ejn of g. And of course, these things are all 0 or 1. So this leads exactly to the Moyal stuff.
Okay, it exponentiates something.
Exactly.
Thank you.
So the only thing that's missing to understand exponentiation is to understand that these intervals are also exponentiate. But because the way I describe the intervals, we'll see that actually, because these graphs only connect on ground vertices, the integrations are actually independent, and all these weights. So the weight of this thing will have to n. That's why the whole thing exponentiates. Which star halves kind of this multiplier multiplication. You can write down the mail. And there's other similar questions you can ask yourself. What about the Poisson bracket? It's linear. It's famous other example of Poisson structures with the 2D algebras. And then you need some of these graphs, but you can have the most vulnerable vertex. That again severely restricts the class of graphs, and people have and doesn't calculate the conceivable quantization of the algebra to the classical quantization of universal entropy. And there's some interesting twists, so you can understand. Very interesting. Excellent.
Check this out.
Okay. So now back to these coefficients. So because you could say, well, now that if I tell you that there is a solution to these operators, you could say, well, let's just write down an arbitrary ansatz with these operators with any coefficients. Then you plug it into this associativity constraint. You work it out. You get a system of equations. And the question is, how do you solve the system of equations? And as I said, it's a very difficult system of equations because it's linear part, it's a quadratic part. And the problem is maybe if you make some bad choices at the beginning, maybe you can solve it later on. So it's quite tricky. So the amazing thing is that you can give an explicit solution to the system. And it's, I mean, I find the solving very beautiful. It seems so simple when you write it down. So what do we do? The presentation of the graph is very suggestive. There's things on the ground, there's things above. So what do we do on the ground? We have the two blue vertices, one is 0, one is 1. And all the other vertices move around in the upper half plane. And they move around all over the place, all configurations in the upper half plane. And then for every edge, we measure an angle. It's slightly twisted thing, it's kind of hyperbolic angle. You can identify this as a, so you have the hyperbolic triangle between I, J, and infinity, and measure an angle. Anyway, it's a difference of two angles, right? So it's the angle between J and the angle between I and the corresponding J. Okay, so that's a little differential one form. Okay. Now we have two n edges because every internal vertex is two edges. We have two n edges. You can wedge all of these together, get a differential form of degree 2n. And we're integrating over all the positions of the constant upper half plane, right? Every point is a real imaginary part, so the domain of integration is exactly the dimension of the differential form. So this has a chance to be meaningful integral. And you can indeed show that this thing converges. There's some things to check, but you can show. And it gives a real number. Because we're just integrating some angles. You get some little real number. Now there's some twist to the story. You can change this angle a little bit and find some other quantization. So this is the original one of the quantization focused on that paper. And the claim is that if you use these coefficients, then you get a sum. Now, of course, this quantization is a big business. There's many interesting twists and directions of this. And I only want to focus on number theory. So I apologize, all the fans of polynomial parts quantization, but I really only want to talk about these things. And my main goal is to understand, explain how that is it that for these integrals you get they fulfill some system of equations. And the second point I want to explain is what are these numbers? How do we compute them? Why are they interesting? You already know they're going to be multiple zeta by slope. Right. So I think best example is to compute one. So this is a full calculation. You can give it to undergrad. I think complex calculus. But it already illustrates some. So let's say we want to compute the first term that has to be computed. We only have this one graph. So what is the integrand? And so, we have one internal vertex. So we integrate over the upper half plane. Just one point. We do a function of one point in the upper half plane. I call its coordinate z. Z bar is its conjugate, and I write the integrand in this particular form. So remember, we have two angles now. There's the angle between 0 and z, and there's the angle between 1 and z. So I can write this. This is the angle between 0 and z. This z over z bar divided by 2i. And this is the angle between 1 and z bar. These are literally the two angles between the real line and these arrows. And we're supposed to wedge them together and take the total differential. So if I take the d of this, if I turn this log into a d log, then I have exactly the integral. I've written it this way to already suggest that you want to use Stokes' theorem. And so the integrand is the wedge of two d logs, but I can integrate the d logs to the log. And then I already see I want to use Stokes' theorem. So this is all about Stokes' theorem, but it's a slightly subtle version of Stokes' theorem. So what is the problem? Well, the problem is that this thing has singularities. And this is not well defined at 0, it's not well defined at 1, it's not well defined at infinity. So actually we can't really integrate over the upper half plane if we want to apply Stokes' theorem. We first have to cut out the little holes around the singular points. Then we get this manifold with boundary. And then we can apply Stokes' this thing. And then we get this mathematic equation. So the idea is the integral is the integral over these things when you make the small circle small and big circle big. That's the limit here. And then on this thing you can apply Stokes' theorem and turn the integral alpha into purely this boundary curve. And then in the end you take the limit here. And this is important because actually it's not even a manifold with boundary, it's a manifold with corners. So actually these individual integrals over these individual pieces, they may diverge, and it's only the sum that the differences cancel. So it's quite subtle if you want to do it in practice, but in this case it's easy because I've chosen for you a very convenient primitive. Because if you look at this function now, z over z bar, d log z minus 1 z bar. That's all is the z is on the real line, that is equal to z bar, the form zero. You don't get any contributions from this real line strips. When z goes to 1, there is a potential issue here with the d log, but the logarithm goes to 0. So that kills any contribution there. When z goes to 0, but we have a problem that this is ill defined, but it's an angle, it's bounded, and this is fine. And so and make the radius small, the integration thing goes to 0. Long story short, we only get a contribution from infinity if that shows this particular primitive. And when that bar goes to infinity, well, actually you don't see the difference between the angle z0 and z bar and z1. So you can replace this just by d log of z over z bar again. So the integrand is turned into log times d log. So it's just a half log squared integrated. So you're only integrating with the subset of infinity. And then the angle is the I pi, but with z over z bar, it goes to 2i pi. All of that over is 1 half. Of course, you can compute this in many different ways. Maybe this is not the way you would have computed it, but I think it's the right way to compute this kind of integral and get a half. And that's great. This means the whole thing makes sense. So what is now the first term of the Dirichlet's formula? But we only have this one graph, so you have to take its graph and its weight, and its weight and its differential operator. The weight is a half. And this is a very easy differential operator, right? It's a special case we had on the board. It's just a Poisson bracket, one derivative from g. This is a very complicated way of writing down the Poisson bracket of g. And it comes with a half. If you take the commutator, you get the Poisson bracket. And so this has to be a half, otherwise the thing is not doesn't fulfill one of the requirements. Now this idea of using Stokes' theorem, this is used by conceivers to prove that this is a star product. So in general, of course, it gets more complicated. You have a moduli space where these points move around, and you have to compactify it correctly. You get all sorts of boundary strata. Then it is as soon as you have a manifold with boundaries, you can apply Stokes' theorem, and then you get these kind of relations between restrictions to different strata. And you can show that these relations are exactly the relations that guarantee you the associativity of the stuff. More generally, this something called formality of being a Slavoj is only special case. But what are these? But now I'm into number theory. So what are these weights? From a quantization point of view, it could be done here. You don't care about whatever weight is as a solution, and maybe you know the modulus as a solution. But as a number theory person, you want to know. That was my question, and what got us interested in this business because the paper was from 1997. There wasn't much known about these integrals. So small ones, obviously, you can compute in different ways. And these are the ones that I mentioned to you earlier at h bar 1 with 1 to h2. And you know, you get some nice little numbers. If you're inclined in a certain way, you might start to meditate on this count. But I urge you not to waste time on that, because there are things where it's just not a rational number. So this was a important paper by Felder and Wilbacher, where they exhibited one graph where they didn't compute it exactly, but they managed to show that there is a non-zero multiple zeta 2 squared, like 6, which for all intents and purposes we can assume is at least irrational, probably transcendental. It's not this one, this is a different graph. Anyway, so there are these non-rational examples. Okay, so then
Are they all uniform transcendentality?
yes, so that's the point that you see here. So the conjecture was that these are always multiple zeta values, and indeed what we managed to show is that indeed if you take a graph with n internal vertices, then you can write it as a rational combination of multiple zeta values divided by the powers of 1 pi. So what is the multiple zeta value? So an ordinary zeta value is just the sum of the inverse powers of positive integers. And for the multiple zeta values, you just generalize the sum to integrate nested sum. So the order tuples of integers raised to certain exponents, that's a multiple zeta value. There's a huge literature and they show up in all sorts of places that associate Feynman amplitudes, information quantization. And these numbers fulfill lots of relations, but it has been found that empirically all these relations preserve the sum of the indices. You would, for example, you could imagine that zeta 4 is something to do with zeta 2 squared, which is indeed the case because zeta 4 is pi to the power of 90, zeta 2 is pi squared 6. So this is an imaginable relation, but you should not expect that zeta 2 is related to zeta 3 in any rational way. So we assume that the weight is a grading on this thing. And then what you do here, you take the zeta value and divide it by exactly the same numbers of i's. So you would call this transcendental weight 0 actually, which corresponds to these rational numbers until you have zeta 3 squared pi to 6. So in some sense, it would be a rational number if for weight reasons, but it's not. So this is.
So is it clear that these are real numbers? Because
So this is an extra ingredient. So what we proved is slightly more general here. Because I briefly mentioned that instead of taking this real angle, you can slightly change the angle and define a different propagator. These are called. So to go back to say. So this thing in this one form is often called the propagator. And actually in a certain Poisson sigma model it is propagator. But you can change this into something that's not real anymore. But still gives convergent integrals. And it is interesting because you can generate a different quantization from different ways. And what we've shown is that it's not just these particular weight integrals we get multiple zeta values, but the more general class of integrals. Basically, every integral you can write down where the integral is a wedge of d logs of z minus z bars, as long as it converges, it evaluates to this. Now, if you take the conceived traits that are written down with a real propagator, then of course you get a huge set constraint because this has to be real, so S has to be even. And this explains why these things are rational. No. So for example, if you you cannot have s equal 1 because zeta of 1. But you could have s equal 3, zeta 3 over I pi cubed. But it's not real. What else do we have? We could have zeta 4 over pi to the 4, but all zeta 4s and zeta 2s and zeta 1 3s, they're all proportional to pi to the 4. Okay, so what about zeta 5? Well, again, it's odd, it would be imaginary. So 6 is really the first time you can write down something real that is zeta divided by the same power type. And so this theorem implies that up to h bar to the fifth everything is rational. You have to go to at least 6 vertices. That's already where you see it. So that's you see the zeta was exactly what you expect.
Do you have any imaginary values? I mean, graphs with imaginary.
I mean, the same graphs. I mean, with the weight that I've defined using this real angle, everything is true. But you can define different ways using a different angle, which is not an angle. It's a log, d log of something, which does not have modulus 1. So it involves the 2 pi I involves imaginary. There's a different set of weights, very similar integrals, but they give imaginary or complex, in general, complex numbers. And indeed, if you do that already with 3 internal vertices, there is a graph with zeta 3 by. I mean, I can draw. So we computed this explicitly as an example in the paper, but I think it was this one. There's 3 internal vertices. And this gives zeta 3 over I pi cubed. But the general experiment is we take a random graph, we don't have all that. A special graph may have one missing here or there, but there's not a huge structure of the constellation. So actually, this conjectured that if you take all of these weights, you get all of the zeta values. So in this case, of course, only the even weight ones. But the conjecture is if you take this other propagator, where you also get zeta 3, then the conjecture is you get all the MZBs. So there's a connection to this moduli space of quantization formulas, which is known to be GRT. GRT is expected to be the more color state models. There's a chain of ideas of why it is plausible.
Co-product of these graphs.
Huh?
Co-product of those graphs that are compatible with.
There is no coaction formula for. I mean, you can already see it here. There's a problem. You have a graph that involves zeta 3 squared. You would have a coaction. Would have to be a term that has zeta 3. Zeta 3 is a Galois squared, but not here. So that's why, indeed, that is another indication why this real weight that comes into is not quite the right way to think about it typically. Typically, you want to have a coaction. You want to have zeta 3, not just zeta 2 squared. You're better off with the others. But some of these are real, and that's not. Okay. So these things are zeta values. And I just want to explain roughly what the strategy is and what is one ingredient that we have not seen in the previous calculation. So I'll do one more calculation for you. It's going to be fine. It's going to be even easier. Oh. So I want to compute this, the integral on top. So I want to integral over the entire complex plane. So no problems with the hard line. Just an integral over the complex plane of the 2 form given by dz bar over z bar, which dz over z minus 1 minus dz over z. Why? Okay. Suppose I want to compute this integral. First of all, take it for granted. I tell you it's convergent. Makes sense. It's maybe not obviously immediately clear, but let's pretend we get through that. And obviously, I want to use Stokes again. So what I do is, well, first of all, I notice, well, all I have to do for Stokes is I write the integral as a derivative or something. So I leave this part as it is, and I just turn the dz bar over z bar to log of z bar. That's fine because this is already homomorphic, so this is indeed a primitive. And now you say, okay, I'm fine. Let's do Stokes. But the problem is, it doesn't make sense. Why does it not make sense? Because log of z bar is not well defined. There's no monotony. Because you have this whole, you have these singularities, right? You have singularities, this thing has singularities, 0, 1, p. But in particular, the problem is with 0. So if that goes around 0, this log picks up a 2 pi, it's not well defined, so no sense to apply sub c. So then the ingenious little trick is, well, let's just redefine, choose a different primitive and add a log of z here. Now we're talking about log of z absolute value. That's you have to think for a second, why does this not change the integral? I just added a term. But this statement is still that this is still a primitive, the derivative of this is still this form. Because I just added something purely holomorphic. Cannot have it. So we first construct a naive primitive, whatever primitive we have. Then we adjust it by purely holomorphic terms. Don't change the fact that it's a primitive, but it makes a single value. Then we can apply slopes. Then we do the same thing, right? So you have to cut out and then apply. Now we have nice manifold boundary corners. Then we can apply these limits and things. And things are very easy, right? So you have this log absolute value squared. And now you're integrating this line integral along this. It's like a residue integral. Just pick up residues of z equal 1 and z equal p, like up here. The thing at infinity actually cancels two terms. At 1, of course, it's 0 because log of that equal 0. All you get is log of absolute value. So this is the main idea here. You just want to use Stokes' theorem, but you have to be careful to get rid of potential monotomies. And of course, in general, when you go to high weight, you have multiple polymorphs, you have to be quite systematic about how to do things. But the long story, this is basically. I just wanted to point out one thing that is important to keep in mind in these kind of situations. Right? If I look at the integrand here, it's a holomorphic function of p. There's no p bar here. Integrate a holomorphic function of p. But the thing I get is log of absolute value. So you might be surprised by that. Normally, if you have a nice behaved convergent integral and the integrand is holomorphic, then the integral itself is a holomorphic function. But these kind of things easily break down. I mean, the problem here is that the manifold you're integrating over moves around when you're moving p around. You have to do these cutouts and you have infinity. So I'm just trying to say you have to be careful with these integrals. Something else that Jens mentioned at the top. If things are not compact, paying attention to the proper calculus is important. So you can have holomorphic functions that integrate to normal.
And a related question. So the primitive, the two-dimensional conformal field theory, the second derivative. If you differentiate one over z with respect to z bar, that's not 0. That's a delta function. So it's
Because you view it as a kind of distribution.
Yes.
Yeah.
That's this.
This is functions. Well, you could maybe say maybe the fact that I'm cutting out and getting residue, maybe you could provide some kind of distribution. But I'm doing calculus 1, 2, and some calculus. These are just functions. I mean, it's completely wasting out. If somebody says d of something holomorphic, I never understood that. Maybe you can explain to me what do people mean by they write.
Well, it's related to Stokes' theorem.
Yeah, but the thing is, you have to say what you're talking about. I don't know what a function or distribution. Here I'm talking about functions. And for me, the whole derivative of dz over z is 0. But you're right. It means I have to cut out something and that's reducing the residue. Almost at the end. I can't remember if I wanted to say anything. I don't want to go much into details. So this is just some sketches. So if you really want to do this systematically, you use the function space of polylogarithms, hyperlogarithms, which are iterated integrals. So you think of the logarithm as the integral of dz over z, and then keep integrating, can create a space of functions. And the multiple zeta values are the values of this function. So there's the connection between these polylogarithms, which you get in the integration process to construct the primitives, and at the very end, you value everything. You only have 0 and 1 and 2 points in the real line over. This is how you get your zeta values. I really don't want to much into detail. The main idea is first worked out by Francis Brown for special case. And some of the holomorphic and endomorphic parts do not talk to each other. You can write down linear combinations of holomorphic and endomorphic polylogons. And if you pick their coefficients correctly, then you can make sure that the monotomies cancel. It's actually well defined and single valued. So there's a space of single valued multiple polylogons that you could use to do the calculation beforehand. And there's a space called single valued multiple zeta values, which are the special of those. So maybe you've heard this last week. I think Brown mentioned this one. I'm just mentioning this because I talked about single valuedness, killing monotony, and here. But those integrals are not single valued multiple zeta values. Because we're talking about single valuedness on the upper half plane, whereas this is single valuedness on the complex plane. As if I'm telling you that the function is single valued, it makes I have to tell you about what subspace we're considering. Where is it single valued? And so our functions here, they mix z and z bars. They are single valued upper half plane. So this is why you actually get all the zeta values, not just the single. So if you have not thought about single value, forget it's fine. Just the bottom line is that if you're integrating d-log things, then the bars, it's somehow an area integral dz bar by this formalism, somehow essentially turns into a factor 2 pi I from a residue and a 1/4 line integral. Somehow, even though you have 2n integrations at the beginning, you only get zeta values of weight n. You're turning this 2n complex integral into an n-fold 1 line integral. That's very reminiscent of this open closed genus zero string amplitude relation. Basically, this idea of Schnell's on the single integration. Yeah, and then as I said, that's proof you just iterate. If you look at integrate one variable at a time at every step, you make a single valued, integrate out in the next step. And at the very end, you're left over with only the function 0, 1, infinity. Basically, that's the definition. That's all I wanted to say. Just think the main steps is integrate one variable at a time. You can find primitives using multiple polylogarithms. These multiple polylogarithms are naturally the Euclid functions in the multiplex space. Zero curves are just a bunch of points moving around. And the idea is that if you think of z and z bars as different variables and you restrict conjugates, then you're working with functions which on that subspace are single valued. And then you have to apply this regularized Stokes theorem. You have to make sure that you take account of different boundary components. You have to regulate, as I said, because then we have these corners, real line, the individual integrals actually all divergent, and you have to make consistent choices of tangential base points and so on. So it's all a bit annoying, but the main idea is just a simple calculation. Okay, so just to summarize, the deformation quantization tries to go from classical mechanics to quantum mechanics by focusing on the product of the function space, so the space, which is somehow supposed to become non-commutative. And the only explicit formulas we have somehow involve transcendental or at least particularly transcendental numbers, like zeta values. Like a baby case of this, we come across quantum groups where the quality of Binfeld associated with KZ connection. Already there, it solves a natural problem, but the only solution we somehow have involves zeta values. Even though you can prove that there are rational solutions. Also here, you can prove there are rational multimorphisms. Just cannot write down. So these things are meant to be there. Just to summarize, so this is like 90% of what I talked about is considered just so our contribution was only this integration. Conceivably work was the fact that we have this nice graphical formula for the quantization, at least as a formal power series, a crossover bracket, and get these weights which are not zeta. Of course, there's future avenues. I don't know. Yeah, so one question that we're currently working on is the idea of making these things typic. So there's this idea of importing more algebraic geometry to enrich this number theory here and make some of these connections between quantization formats in this modularized space and Galois theory of transcendental numbers of size. So this involves trying to construct algebraic geometry models like varieties whose periods would then be these integrals, which is a bit difficult because start with the upper half plane, which is not quite a variety. Some of the measuring powers will be bigger than 0, or something quite algebraic geometry as well. So getting a proper algebraic incarnation in this typic sense is proving quite tricky. But if you could do that, then there would be this motivic algorithm that sorry, I have no time to explain that in detail. But if you've heard about the motivic algorithm, you would like to apply it in this case. And then you could act on every zeta value and create a new quantization formula by treating the zeta value as a parameter and substituting it. But maybe let me stop here. Thanks.
There were a number of questions already. Are there more?
So once you constructed the star or does the resulting have any sort of natural small?
Yeah, so I mean, I think people have studied this for algebraic setups. So if you have a Poisson structure that is a little polynomial, on the right hand side of the Poisson structure, into the Poisson bracket are polynomials, then you could imagine a situation that you can describe quantized algebra, generated equations. And there are examples of that. So there's even a way to construct quantizations directly using this approach, generated equations to return.
So I was asking about like if there's any sort of natural modules or this start this new algebra.
Oh.
Yeah.
But there are actually there's a you can enrich that quantize not just the function. I just say I don't. Yeah, I'm gonna say it.
There are many relations among those multiple zetas. You have a way family of those maybe to picture them. What graphs those like?
That's right, I think I have the relations. Yeah, so just for people who have not seen them, this is just an example of all the zeta values in no ways you can write down. And funnily, they're all no ways, they all seem to be dependent on coefficients. And this is a table where I wrote weight and then generators for the vector space. You take all zeta values of the weight development, use all the relations. Then it turns out there's not much left over. In particular, the only real ones that you see beyond trivial one is at weight 6. And then the interesting case is this weight 8. The zeta value people, they're always very excited at weight 8. There's zeta 3,5, which is a zeta value which trajectory is not represented as normal. And you might ask, but does it show how? And it does show how. So, as I said, the conjecture is that you really get everything. And we've done so order 6 is the one until then we have completed all that. But then at higher orders, it just completely random bunch. And we don't have to compute many to find it. And they are there, and I think also at weight 9 and 10 check. Beyond that, the integration gets but I have not written down these. Problem is there's quite a lot of graphs for vertices. It's 300 something. And they're all rational numbers. And there's a gazillion ways. So the problem is the way that the integration works. It doesn't really give you a preferred way to write this as a multiple zeta, right? So it's some multiple zeta, like even with integer coefficients actually. But it depends on the order of integration. So if you would have integrated another order, you could get a different expression out. I mean, you know it's the same. So you could actually ask, yeah, you can generate relations among zeta values by running the algorithm for the same interval, different orders.
There's no natural way to.
There is no natural way. But I agree with you that this thing generates some relations. And I have not tried to look at them. My project would be with all relations.
There's this model on way to that.
But it's definitely in there somewhere.
So, could you-
Is that
12 is too far.
I don't know, it's going to be very messy. So, I mean, one way to think about this. So what is this Stokes thing doing? Yeah, it's taking this interval of over a surface, and turns it into a line interval. You do this again and again and again, and at the end we have the iterated interval, you have your zeta value, you can see associated coefficient. So in a way, this is a machine that expresses every weight of the graph as a highly complicated combination of associated coefficients. But the way, first of all, it's very complicated, very interactive, just write down generating series. And also depends on several choices of who you take. So it does make a connection to relation among the universe themselves. So not the kind of thing you just open your eyes.
Is there an example similar? Well, the real product that you gave us only generates rational coefficients. Is there something, a choice of propagator and a choice of symplectic structure that only gives you single zetas?
I wouldn't have come across one, and
So in particular, the diagram that you wrote over there, does it just produce zeta 3 or it also
You mean
produces
this one?
rational? Yeah,
it also has a rush.
I see.
Oh, you want to get rid of the
Yeah,
no.
I was thinking if it exponentiates, but only like say beta solution period, where you only have like odd zetas.
At the moment, I don't understand the relation between the graph and its combinatorics and the number theory. At the moment, this is a mystery. I take the graph and something comes out. But I couldn't tell you in advance, okay, there's zeta 3 here. And there's a double zeta, and that's because of that would be amazing if you could really make this connection to graph by graph level. Say there's some funny collection where like that's like maybe that's possible. I mean, the fact that you have this geometry behind it. But what's slightly misleading is that the graph itself is just one way to pick out some differential. And there's relations now. You can write down many different graphs. Maybe the linear combination is a differential form of zero. This is like kind of a loose point. The graph is nice complete. And we've done calculations of cohomology groups. And if you look at the cohomology groups of these moduli spaces in the way that we're thinking about, we're not too much into it, but there are cases of differential forms you can write down, which integrate to nice numbers, which are in this framework, which give zeta values, but which cannot be written in terms of graphs. So the graphs are two things. First of all, they have relations. They also don't generate full homology. This makes it quite questionable whether you can really capture everything in these graphs.
But also there is the Poisson structure as well, right? Because the graphs that you compute there is everything. But then I can select a particular Poisson structure with something that cancel.
This indeed. So already seen
Yeah,
example.
Traditional example.
Actually, when you take a specific Poisson structure, it's embarrassing how little we know about phenomena we see, because I mean, just one example. So this is log canonical bracket. Yeah. Then R2, obviously x with x and y with y has to be 0. And you take x comma y, the x times y. Yeah, so we said if you have constant Poisson brackets, you get well. If you have linear ones, it's related to the algebras. like having quadratic entries in the Poisson bracket, like the next interesting case. So this one, what happens, we compute the subproduct what I started with 6, you see the 3 squared shows up. Because if you look this up, maybe it's in the individual graphs, but it cancels out subproduct. Now for this one, it doesn't. It shows up in the subproduct. But when you compute the algebra, quantize the structure of this quantized algebra, you can transform it away. And you can write it down without anything. And to this day, as far as I know, we don't know of a single example of some structure where you would really need the zeta values and we see it survive. Yeah, it's very frustrating. So it's very complicated. Well, one side of that story is that on the formal level of quantization, this individual formula, this individual components are not really such a meaningful. You're looking at the modular space, there's the trivial transformations where you can transform away certain terms by changing coordinates and this kind of thing. So that's why we shouldn't treat every zeta that shows up as being physically, but none of this is physically useful, not even mathematically necessarily. But some of them are, but not all. Sorry, this is probably useless. I don't even understand that.
Thank you very much. Good ending point, I guess.